Introduction. Stars, including Sun, galaxies, extrasolar planets, interstellar medium, cosmic microwave, background, etc., are main fields of study in astrophysics. Emissions of all these elements, or say objects, are examined in astrophysics. Such examination is done across all parts of electromagnetic spectrum. Properties of such objects are also examined. Some major considered properties in astrophysics are luminosity, density, temperature, and chemical composition. Since many of the physical concepts are applied, astrophysics is a very broad term. Following physics concepts are applied in the field of astrophysics: mechanics, electromagnetism, statistical mechanics, thermodynamics, quantum mechanics, relativity, nuclear and particle physics, atomic and molecular physics. When it comes to practical application, a substantial amount of work in theoretical and observational physics are often involved in modern astronomical research. To determine the properties of dark matter, dark energy and black holes, efforts are invested by many areas of study in astrophysics. Studies of astrophysics are based on multiple assumptions: origin and ultimate fate of universe, possibility of time travel, formation of wormholes, and existence of multiverse are some of the most important assumptions. Following areas or concepts are studied in theoretical sector of astrophysics: solar system formation and evolution, stellar dynamics, large-scale structure, matter in the universe, origin of cosmic rays, general relativity, physical cosmology, string cosmology, astroparticle physics. Physics of the universe are studied in the astrophysics, as the name already implies. Astrophysics is a large term and covers almost every important object from space and ultimately the universe. Scope of the astrophysics covers stars, planets, and even galaxies. As described above, astrophysics is a combination of physics related to universe or astrology. Both astrology and physics are broad subjects with a number of descriptive concepts to cover. It makes astrophysics a comparatively broad term. Many disciplines of physics are applied to multiple concepts, sectors, and objects that fall under the scope of astronomy. It even stretches the term even longer. Astrophysics is widely applied by most of the space centers in order to determine the new planet's arrival. It is also used to acquire more knowledge about particular knowledge. For instance, capacity of the planet and various resources available on those very same planets, whether conditions of that planet and existence of life on those planets can be determined by practical applications of astrophysics. Concepts of astrophysics are majorly important in the area of exploration of universe. Principle of momentum conservation and angular momentum were developed by Newton in the field of mechanics. Newton was an unorthodox yet highly religious personnel. He produced noticeable work on biblical hermeneutics compared to natural science. However, he is remembered for his work in natural science today. In the Poll of Rules Society in 2005, Newton was determined to leave more influence of history of science compared to Albert Einstein. Chapter 1. History of Astrophysics. History of astronomy is being recorded since ancient times. Studies of terrestrial physics have been always separated from the field of astronomy. Aristotelian worldview is an important concept related to astrophysics, according to which bodies floating in the sky are unchanging spheres. Motion of these unchanging spheres, a uniform motion, is circle. On the other hand, the objects belong to earthly realm were recorded to went through growth and decay. Natural motion of these objects was not in circle. Instead, it was in the form of a straight line. This motion tends to end whenever its relative moving object reaches to its final goal. Eventually, it was also discovered that the celestial region holding these objects was fundamentally formed of a different kind of matter. Discovery of this kind of matter eventually leads to foundation of terrestrial sphere. eventually lead to foundation of terrestrial sphere. For instance, it was discovered that Plato is maintaining the fire and Aristotle is maintaining the ether. In 17th century, many natural philosophers such as Galileo, Descartes and Newton put their efforts in order to discover that the regions of celestial and terrestrial are formed by similar category of material. They also found that same natural laws are applied on both of these regions. However, they soon faced challenges in order to prove their assertions practically. They were lacking the tools that could prove their assertions in practical manner. Although these tools are available today, they had not been developed in that era, which was giving Hole a lot of troubles towards the researchers of this field. Throughout the 19th century, most of the astronomical research was dedicated to measure and compute the positions and motions of various astronomical objects. In the same era, William Hyde Wollaston and Joseph von Fraunhofer invested their efforts and tried to decompose the light of sun. They managed to discover a region that was formed as a result to multitude of dark lines in spectrum. This region has very less or no sunlight. This discovery gave birth to a new stream or branch of astronomy that is now known as astrophysics. By the 1860s, famous physicist and chemist Gustav Kirchhoff and Robert Bunsen made some fascinating discoveries and established new foundations. They observed that dark lines that are present in solar spectrum are strongly related to bright lines. They demonstrated that bright lines are present in spectra of known gases. They also described that some unique line among these lines are strongly correspond to a specific chemical elements or unique group of elements. Kirchhoff discovered that absorption caused due to chemical elements in solar atmosphere results as dark lines. This foundation eventually proved that elements present on Sun and other similar stars are also present on Earth. Norman Lockyer was one of those many theorists and researchers who invested their efforts in studies and researches in the field of solar and stellar spectra. In 1868, Norman Lockyer was studying about solar spectra. He discovered dark lines and bright lines as well in solar spectra through his studies and research. This was a relatively small discovery. However, it is considered majorly important since it provided a much required breakthrough to a new branch of research and studies. During this short study period, Norman managed to leave his name on the history of astronomy and history of physics as well. His researches are now useful in both of these fields of study. In researches of Norman Lockyer, well-known chemist Edward Frankland played a major role helping him in order to investigate the spectra of elements. They repeated their investigation on various temperature and pressure levels. He concluded that it was not possible to associate the yellow line in solar spectrum with no available element. He finally figured that this yellow line was representing a new element. This newly discovered element was given the name helium after the Greek word helios. Personification of Sun was finally completed. At Harvard College Observatory in 1888, an ambitious program was undertaken in order to conduct further researches on stellar spectral classifications. Edward C. Pickering was the main face behind this project. A team of women computers was dedicated to the project, mainly consisting Williamina Fleming, Antonia Mori, and Annie Jump Cannon. The goal of this team was to classify the spectra that were located on photographic plates, which they managed to do successfully by 1890. By 1890, this research program managed to prepare a catalogue consisting of over 10,000 stars. These catalogue groups these stars in 13 spectral categories or types. In 1924, Cannon followed the Picketing's lead and continued his work in direction of expanding the catalogue. He managed to expand the catalogue consistently and continued his work until he had already achieved 9th volume of the catalogue. At this stage, there were over 250,000 stars in the complete catalogue, consisting these 9 volumes. The catalogue was later developed to Harvard classification scheme. In around 1922, this scheme of classification achieved worldwide acceptance. The Astrophysics Journal, an international review of spectroscopy and astronomical physics, was established in 1895. Main faces behind this journal were George Ellery Hale and James E. Keeler. They were working along with a team of 10 associate editors originated in Europe and United States as well. Intention of establishing this journal was to fill the gap between journals in astronomy and physics. It is accepted that this journal will merge both these fields. It provided the venue that was required in order to publish articles based on astronomical applications in the field of spectroscope. It published many important contents, such as laboratory researches on astronomical physics, determinations of wavelength, metallic and gaseous spectra, and experiments related to radiation and absorption. This journal helped a lot to let people know about modern researches related to the Sun, Moon, planets, comets, meteors, nebulae, etc. It also brought instruments such as telescopes and laboratories to light. In the year of 1925, Cecilia Helena Payne took a memorable step in the field. She is also known as Cecilia Payne Gaposchkin. In 1925, at Radcliffe College, she wrote influential about doctoral dissertation. In that influential, she described how she experimented by applying ionization theory on stellar atmosphere. She further added that she intended to relate spectral classes with temperature of stars when making such experiments. It is significant that she was the one to discover that main components in the structure of most stars were hydrogen and helium. This discovery was all of a sudden and surprising for all related to this field. She was convinced by her readers to modify the conclusions before releasing her writings publicly. However, later on, researchers confirmed that her discovery was legit and nothing but plain truth. As a result of new leads provided in the field on quantum physics, the research in the field of stellar and experimental spectra managed to advance even further. In the next chapter, we will be discussing observational astrophysics, that is an important category, or say sector, in the field of astrophysics. Chapter 2. Observational Astrophysics. Observational astronomy is one of the most important sector or classification of astronomical science. Observational astronomy is dedicated towards recording data. Researches and observation in observational astronomy are based on contrasts with theoretical astrophysics. Here, it is noticeable that theoretical astrophysics is mainly dedicated in order to figure out measurable physical, a model for which practical implementation is possible. Observational astrophysics is simply a practice in which celestial objects are observed with the help of scientific instruments such as telescopes and other apparatus that are usable in astronomical field of study. It is noticeable that most of the observations made in the field of observational astrophysics are based on or done with the help of electromagnetic spectrum. A wavelength that is greater than a few millimeters is useful to radio astronomy in order to study and research about radiation. Radio waves are treated as example areas in such researches or studies. These radio waves are usually emitted using cold objects. Interstellar gas and dust clouds are great examples of cold objects used in such researches in order to emit radio waves. Redshifted light that is generated through the event of Big Bang acts as cosmic microwave background radiation in such experiments or observations. Pulsars are the first ever objects that were detected at microwave frequencies. A very large radio telescope is required in order to conduct study of these waves. In infrared astronomy, radiation is studied with a wavelength that is long enough to be visible to naked eyes. However, it is made sure that these wavelengths are not longer than radio waves. In simple words, these wavelengths are longer enough to be visible to naked eyes, yet shorter than radio waves. Telescopes that are used in infrared observations are much similar to normal optical telescopes. Objects colder than stars, mostly planets, are mainly studied at infrared studies. The oldest kind of astronomy is optical astronomy. In this kind of astronomy, telescopes are paired with charge-coupled devices that are also known as spectroscopes. These are the only and most common instruments used in optical astronomy. However, Earth's atmosphere is one of the major problems in such optical observations. To ensure highest possible image quality, adaptive optics and space telescopes are used to avoid these limitations, or at least make them less affecting. Stars are highly visible in this range of wavelength. In optical astronomy, it is also possible to study the chemical composition of the stars by observing chemical spectra that are highly visible too. Along with stars, this kind of observation also helps to understand and study chemical structure of galaxies and nebulae. Binary pulsars, magnetars, black holes and many other super-energetic processes are studied under ultraviolet astronomy, X-ray astronomy and gamma-ray astronomy as well. Earth's atmosphere is not penetrated by such kind of radiation well. Electromagnetic spectrum can be learned in two possible ways. First one is the space-based telescopes and second one is ground-based IACT. Here, IACT stands for Imaging Air Cherenkov Telescopes. RXTE, Chandra X-ray Observatory and Compton Gamma Ray Observatory are examples of space-based telescopes. On the other hand, High-Energy Stereoscopic System, or HESS, and MAGIC telescope are well-known examples of land-based IACT. There are only few other things originated on great distance that may be observed from Earth other than these electromagnetic radiations. Gravitational waves are extremely harder to detect compared to electromagnetic radiations. However, a few gravitational wave observatories are constructed with a hope to achieve new leads in the future. Some observatories are dedicated only to the observation, studies and researches related to Sun. Such observatories are known as Neutrino Observatories. A limited number of them are scattered around the globe in various countries. It is possible to observe cosmic rays that are holding a significant amount of energetic particles. They are often hitting the atmosphere of Earth, which makes them highly detectable. Time scale of these observations greatly affects them. The amount of time required for optical observations varies between several minutes to hours. Thus, it is certain that phenomena cannot be readily observed by optical observation if it is changing faster than that amount of time. However, historical data on many objects and centuries and millennia can be found and is available for studying. In the same way, radio observations are capable of observing events on milliseconds or even that last more than a year. For example, pulsars and pulsar declaration are studied under radio observation. It should be noticed that pulsar keeps changing on a timescale of milliseconds, where pulsar declaration is a process that can last more than a single year. Information acquired from two various timescales will certainly be very different, even if it is related to a very same object. Observational physics gives a special place for studies related to the Sun. Compared to any other star in the universe, it is possible to observe the Sun with great details since it is relatively closest star to Earth. Other stars are noticeably far away if compared to Sun's distance. The details observed in the studies of Sun can never be paralleled by the studies of any other star. In fact, the details obtained through studying the Sun helps researchers to understand other stars by using those data as a base knowledge. Hertzsprung-Russell diagram is useful in understanding how stars change of stellar evolution. These topics can be understood by placing a variety of star types in certain positions on this diagram. This diagram is often viewed and studied as a representation of a certain state of stellar object, providing varieties starting from its formation or birth and lasting up to the death of that particular stellar object. Since you have got enough idea about observational astrophysics in this chapter, we will be discussing theoretical astrophysics in the upcoming chapter. Another important yet short concept of popularization would also be discussed in the very same chapter. Chapter 3: Theoretical Astrophysics and Popularization Theoretical Astrophysics. A wide variety of tools is used in the field of theoretical astrophysics. This variety of tools encompasses analytical models and computational numerical simulations. Polytropes used in order to approximate the behavior of stars is a great example of tools used in the sector of theoretical astrophysics. Each of these tools is unique in their own way and with their own advantages and limitations as well. To gain a better idea about what is going on into the heart of a process, using an analytical model is considered and proved to be the best option. Existence and effects of phenomena can be revealed using numerical models. These models are also applied to those effects that cannot be seen without implementing these models. In order to figure out observational consequences of any process or object, theorists of astrophysics develop theoretical models that represent that particular process or object. This process is useful when observers are requiring some data in order to refute a model. It is also useful when choosing between numbers of alternate or conflicting models. It helps to choose the best matching model. Attempts are made in order to modifying existing model or even generating new models that could take new data as input and in account as well. Whenever inconsistency arises, attempts are made to keep the modification at minimal level so that model can fit according to the available data. The reason behind keeping the changes minimal is that the more original the model remains, the more accurate outcome it will provide. A model even requires to be abandoned in situations in which there is a large amount of inconsistent data compared to timescale. Following is a list of most important topics studied in the field of theoretical astrophysics: stellar dynamics, stellar evolution, galaxy formation, galaxy evolution, magnetohydrodynamics, large-scale structures of the matter in the universe, origin of cosmic rays, general relativity, physical cosmology, string cosmology, astropractical physics. In the process of gauging the properties of large-scale structures, astrophysical relativity serves as a tool. In such process, gravitation plays a significant role. It is relatively important in investigating physical phenomena. This concept is important in studies of black hole astrophysics and studies of gravitational waves. Some of the theories of theoretical astrophysics are widely accepted and being studied and researched as well. Their models are also proven to be successful. Following are some widely studied theories and models of astrophysics: Lambda CDM model, Big Bang, cosmic inflation, dark matter, dark energy, fundamental theories of physics. Wormholes are one of those examples of hypotheses that are yet to be proven. However, many theorists disprove concept of wormholes, saying that we would never manage to prove such a model practically. Many of them often question the existence of wormholes. Popularization. Astrophysics began to spring in the 17th century when unified physics was at its fully developed phase. It was the time when various branches of astrophysics were beginning to develop. Same laws of physics were applied on the concepts from both celestial and terrestrial realms. In that era, there were many scientists that were qualified in both physics and astronomy. They were responsible for laying down the basic foundation of a new area of study that is now known as astrophysics. Thanks to the popularization of astrophysics by Royal Astronomical Society, students can continue to be drawn towards astrophysics in modern time. Following educators have a significant contribution in the establishment in field that is quite enough for leaving their name in the history for decades to come. Subramanian Chandrasekhar, Hubert Reeves, Neil deGrasse Tyson, Stephen Hawking, Carl Sagan. Students still got attracted to the history of science, astronomy, physics, and astrophysics thanks to the valuable contribution of many early, late, and present scientists and researchers. This chapter might seem kind of short since theoretical posture of the astrophysics is not as much developed and descriptive as the observational and practical posture. Now, after getting to know with observational astrophysics, the next chapter will discuss some of the most important findings in modern astrophysics. Chapter 4. Greatest discoveries of modern astrophysics. Both physics and astronomy, along with their combination like astrophysics, has went through a long era of development and researches. Many famous astronomers, physicists and scientists have contributed their efforts in this journey, such as Einstein, Bohr, Hubble, etc. If we look at past, discovery of planets and the solar system, figuring out true relation between Earth and Sun, mathematical calculations of planetary orbit and universal gravitations were major discoveries. However, more shocking and important discoveries are made in modern astrophysics compared to past times. These discoveries make us realize how shocking and unimaginable our universe really is. Some of these discoveries were proven in a practical manner. However, some of them remain just theories in hope that researchers would manage to prove them too sooner or later. Dark energy. Discovery of dark energy was made using Hubble constant. We'll discuss in the chapter later. Measuring supernovae of distant stars was also helpful in this discovery. It was found that these distant stars were not getting contracted by universe, and neither they were static as described by Einstein. According to this idea, universe is the one that is actually expanding, and with time, this expansion is even speeding up. To account this expansion, a hypothetical form of energy was purposed that is now known as dark energy. This hypothetical form of energy is now being observed, studied, and investigated by many astrophysicists and cosmologists. According to cosmological constant, dark energy is a scalar property of space-time itself. Some theorists describe it as a dynamic matter or as quintessence. This debate is still in an ongoing form. Current state of astrophysics purpose that 74% of energy in the universe is in fact the form of dark energy. Dark matter. Dark matter is actually something different, a lot of different, than dark energy. It is a type of matter that was proposed in order to explain gravitational effect that is certainly present among various galaxies. Astronomers somehow managed to measure total mass of galaxies. According to their results, they predicted the orbital speed of star within a certain galaxy. However, the actual results were not actually matching expected or predicted results. They concluded that there is a unique matter that cannot be detected using measurement techniques. This unknown matter is known as dark matter. It is said that this dark matter somehow holds a strong relation with electromagnetic radiation, which is yet to be discovered. Cosmic microwave background radiation. Cosmic microwave background radiation is often referred to denoted as CMBR. CMBR is nothing new, but just a form of electromagnetic radiation. It is believed that this electromagnetic radiation was left over in the universe after the event of Big Bang. It was discovered when two of the Bell employees were working with a radiometer for satellite communications experiments. During their work, they discovered an uncountable 3.5 K temperature in excess. They concluded that this heat was generating from the radiation that is left or survived as universe shifted its stage. Thus, it actually belongs to the previous stage of the universe's history. In modern studies, previous stage of universe is simply theorized as Big Bang. So simple, cosmic microwave background radiation is remaining radiation left from Big Bang. Exoplanets. As various planets and non-planetary objects were discovered in the solar system, astronomers started to believe that there are more planets around different stars in the universe. Following such a simple thought, astronomers began to observe and study other stars in order to find new planets, maybe one with life. The research began by observing the light spectra that was being radiated by distant stars. Their brightness, plotted over a certain period of time, was also studied and observed. Following this simple approach, astronomers have discovered a large number of planets known as exoplanets, just to make them sound different from planets of our solar system. First group of exoplanets were discovered in the year of 1992. Those exoplanets were orbiting a pulsar, just like planets from our solar system orbit around Sun. Black holes. Stephen Hawking delivered a lot of research and interesting theories that was enough to make black holes famous among researchers, scientists, and even students. Black holes are described to be a certain region of space. From this region, nothing can escape, not even light. It is because of its unique property known as singularity. According to singularity, black hole pulls massive gravitational force from a single point in the space, that too with infinite density. Other than a flat event horizon, nothing can be seen and nothing can escape. Astrophysicists believe that black holes are formed as a result of large stars collapsing. In such process, degeneracy process of electrons and neutrons cannot be held by even atoms intact. It is also believed by astrophysicists that larger black holes exist in the center of general galaxies and spiral galaxies. General relativity. Albert Einstein is the main face behind this theory. According to the theory of general relativity, gravity is a common property of both space and time. This theory also provides explanations for redshift of light and bending of light, as well in respect to extra-large objects. It has been verified majorly by multiple tests. Solar eclipse provided the most famous proof towards general relativity. During solar eclipse, the light coming from stars was mapped or recorded and then extrapolated in attempt to locate the stars. The result was different than where the stars actually located. It was concluded that warping of the light was the reason behind such difference. Redshifting and the Hubble constant. In modern astrophysics, it is believed that galaxies are receding away from Earth. Hubble developed a law according to which it was possible to calculate speed of these galaxies at which they are receding from Earth. This law simply demonstrates that how galaxies are moving away from us. This law also provided basics for further development of Big Bang theory. Later on, this law was used in order to prove that galaxies are moving away from the Earth, or ultimately from our solar system, with a speed that is actually more than the predictions made by us. This discovery was based on redshifts of supernovae, form or stage of massive stars located at distant galaxies. Gamma-ray bursts. As the name implies, or simply gamma-ray bursts, are bursts of gamma rays that are being radiated from distant galaxies. It is suspected that gamma rays are resulting from super-energetic explosions far in the universe that can even vaporize entire planets. Gamma-ray bursts are considered some of the most luminous electromagnetic events that take place around the universe. Most of the astrophysicists believe that gamma rays are radiated either through supernova explosions or merger of binary in other galaxy neutron stars. However, other than their existence, all other details are just theories, since nothing is verified practically. The age of the universe. Cosmic background radiation was discovered using redshifting measurements. Age of the globular clusters of ancient stars in galaxies is also measured using that very same concept. Using all of these concepts, astrophysicists managed to calculate the age of the universe. It is estimated that while this book is being written, our universe is about 13.75 billion years old. The Big Bang Theory. Astronomers and astrophysicists were encouraged to develop Big Bang Theory thanks to discovery of CMBR, redshifting, and fast recession of the galaxies. Big Bang Theory is currently the most acceptable model that represents the formation of universe. The model of Big Bang does not represent an explosion in space and time. It actually represents the formation of space-time from nothing. Big Bang Theory also thinks about our role in the universe, possibility of existence of other universes. It is also assumed that what if something existed even before Big Bang actually took place. Big Bang model survived plentiful and sort of verifications in order to become a widely accepted model. Inflationary Theory. However, discovery of CMBR, it was proved that temperature is uniform in entire universe. On the other hand, cosmological principle describes that universe is flat, isotropic, and homogeneous. If cosmological principle is considered right, the concept of uniform temperature can never be practically possible due to traditional thermal interactions. Inflationary theory describes that universe was formed with a super-rapid exponential expansions. It also describes that such expansion was caused due to pressure of energy. This energy was possibly the reminiscent of dark energy. However, this theory also accepts that before any inflation, the universe was connected and had a balanced uniform temperature. Chapter 5. Chaos and Complexity in Astrophysics. Astronomy is an independent branch of science. All the bodies and matter scattered in the entire universe come as the scope of astronomy. Origin, evolution, composition, distance and motion of such bodies are studied in astrophysics. On the other hand, astrophysics is often considered theoretical part of astronomy. Physical structure of cosmic bodies is main area of study for astrophysics. It does not only learn about cosmic matter, but also about the universe as a whole. It learns about various characteristics of universal objects in order to form a proper model for them that can simulate exactly what is happening around them. Knowledge acquired in physics is exploiting in astrophysics. Irregularity of large-scale amplitude population 2 stars is more challenging to explain. Large dissipation is implied in the variation that is observed in the pulsation amplitude of a certain period. Thus, existence of center manifold is clearly false or denied. To explain this concept, or chaos, many models have been developed only to be proven impractical or lacking accuracy. One of these many models suggests some unique assumptions. That model describes several pulsations frequencies. It is also described that these frequencies are spaced closely than normal measure. It is observed that such frequencies are hard to find in every stellar model. Their existence is noticed in specific stellar models that possess appropriate properties for their existence. It is also suggested through a different model that these frequencies possess stochastic nature. That kind of nature is followed or possessed by these frequencies in a number of varieties, different properties with same stochastic nature. There has been no mechanics proposed for these frequencies yet. It is also believed that there is no such mechanism exists that can provide equivalent energy for such a large variations of amplitude that are being observed. As a conclusion of the concept, the latest and considerable suggestion is that mechanism responsible for irregular light curves does not exist in our dimension level. It exists in low dimension described in chaotic dynamics. The conclusion is based on more than one theories that come from astronomy as well as chaos theory. Regular behavior of the Suffice. Since 1960s, successful model for regular Suffice behavior have been developed. In theoretical point of view, it is quite easy to understand since center manifold is present. Center manifold arises as a result to dynamical system possessing dissipative nature on weekly basis. It is a fact that pulsations tend to be weak as a non-linear structure. It also allows a system description. This description is provided in terms of amplitude equations. A construction bifurcation diagram is also provided. This diagram refers to possible types of pulsation. It is an important concept in astrophysics also, since it supports an important chaos, or say complexity, in the field of astronomy, physics, and relevant chemistry as well.